Thermodynamics. Here we go. Definition of heat. This is the energy in transit from a hot object to a cold object. I will talk about the misconception on Monday. Which way does heat travel? Naturally, always from hot to cold. Always from hot to cold. We can make it do the other way, but naturally, by itself, some textbooks say spontaneously, always goes from hot to cold. Thermal equilibrium is when two objects have the same temperature and no heat is transferred between them. Okay. Thermal equilibrium is when they have the same temperature and no heat is transferred between them. Good with that? Okay. So today we're going to be talking about the three different ways that heat is transferred. So first way is by conduction. Okay. Do you remember when we were talking about static electricity? One of the ways to charge was by conduction. In order to charge by conduction, you touched. Okay. Same thing here. When objects with different temperatures are touching. So there's physical contact. Objects with different temperatures are touching. Charging by conduction. Okay. Now, microscopically, here's where this comes from. This quick chemistry review. Temperature is the average amount of kinetic energy that molecules have. Remember that? I'm pretty confident you guys, that was pitched to you last year, chemistry. Okay, it's the average amount of kinetic energy. So something that is hot, intermolecules are vibrating more. Something that's cold, they're vibrating, but just not as much. So when you take a hot object and put it next to a cold object, the hot object's bumping into the cold object, like, and it like gives it more kinetic energy, causes it to warm up. Charges by conduction. Good with that? Okay. Okay. I want you to go around the room and I want you to feel different materials. Not anything living, Not anything plugged in. And stay away from that demo table over there. Okay? Different different materials. Different materials. All right, bring it on in. Okay. Okay. All right, bring it on in. All right. What do you say? Okay, so how long have the objects you touched been in this classroom? Well, since probably at least a year because we just got in here. Okay, but a long time. Okay, what happens when objects of different temperatures sit in the same environment over a long period of time? They change, they reach a thermal equilibrium. Hot things cool down, cold things warm up. You go for thermal equilibrium. All these objects have been in here for a long time. All these objects are 69 degrees because that's what the room temperature is set at. Correct answer is E. All the same, right? But why does metal feel colder? Okay, the answer is metal is a better conductor of heat. It has a higher thermal conductivity. Okay? Metal is a better conductor of heat. It has a higher thermal conductivity. What's hotter? You or the things that you touched? Okay? You all. You're 98 point something. When you're touching things, those are all 69 degrees. So which way is heat going? Out of you into the objects you're touching. Okay? So when you touch something metal, heat is just leaving your hand faster than when you're touching wood. Wood is not as good a conductor of heat. Okay? Now, you might be thinking conductor. Is that like electricity? There are some correlations, but it is definitely not a one-to-one thing. They're caused by different things. So metal is a good conductor of electricity. It's also a good conductor of heat. Um, electrical conductors is a characteristic of the motion of electrons. The characteristic, like what makes something a good thermal conductor, is if how the molecules are vibrating, not so much the electrons specifically.
So what is heat like?
So heat lightning is electrical. There's turbulence with the heat. That's good. There's air currents going on, and that's what causes the rubbing the stripping of electrons. Yeah, still electricity. Heat is caused by, um, we'll get to convection here momentarily, but due to clouds moving against each other. And it's a really weird way to say that, but it is still electricity, just due to heat. Like, yeah. All right. So, um, good with that. Leaving your hand faster. So some people can have cold hands versus hot hands. That's just the consequence of your like your circulation in your hands. Um, you can have your hands aren't probably not 98.6 degrees. They're probably something a lot colder. That's why you stick your thermometer. Oh, you guys, you don't do thermometers anymore. Stick them in your mouth.
Why don't we do thermometers anymore?
Oh, I zap my kids now.
I don't even have a zapper.
When you what? Okay, so your body temperature. The question was, how do you get fevers? Your body temperature is a consequence of your metabolism. Like you're burning, you're converting chemical potential energy of your food into kinetic energy of motion, which reflects as a temperature. If you get a fever, that's your body working hard to it ramps up the blood flow to like provide more white blood cells to attack the infection. Um, and the consequence of that is your body temperature rises. Um, and so you actually, if you can prevent not taking medicine, like if it's a low grade fever, you don't want to take the temperature down unless it's like preventing you from sleeping. You want the temperature, the fact that you have a fever is a healthy thing. That's your body responding to the infection. Does that make sense? So like when you have a kid, like, oh, they got 101-degree temperature, like don't give them aspirin to take the temperature down. That's a good thing of it. Like keep the temperature warm. Now 104, 105, 106, that's when you're like, oh, okay, we should do something. Or if they're not getting able to sleep, sleep's a good thing for the body to recover. If that's preventing them from sleeping, then pack them with aspirin. But good to that. So like having a temperature, that's a good response. Okay. All right. A little bio lesson in the middle of physics. All right. So Pyrex is the really thick glass that you can cook in, like measuring cups. Some big measuring cups are Pyrex, casserole dishes, Pyrex. Hey, yeah, go get them, buddy. All right. So, have you ever been cooking something in an oven, pizza, cookies, whatever, and you wanted to check on it? So you open the door and you forget to like move your head back, and you're like, whoa, you're like it, like whoa, that's hot. How hot is that air? Like 450 degrees, whatever your setting of your oven is. Okay. Imagine getting your face engulfed with 450-degree metal. A little different reaction than like, whoa, that's hot. It'd be like, You getting engulfed with 450-degree metal. Okay? Does that make sense? So air has a really low thermal conductivity. Okay? It's still 450 degrees. It just doesn't transfer that energy to you as quickly. Okay? All right. Come on back here. I want you to feel, put your hands on both those, just feel them. Once you registered them, come.
That's silly.
One's metal, one's plastic. You're touching two blocks.
I don't want to be cold.
They're not that bad.
What can I say? I'm like, hardest to find speaking of like the mom. I'm not gonna touch it. I do that all the time. Are they cold? One of them. Freezing. Oh, a little chilly. Just has ice. It's dripping. I already have tissues. Is this like the place that they have like cold stuff? Cool. Oh, yeah, okay. That they make ice cream? Yes. Probably.
Everybody good?
You're smart.
Okay. Actually, we don't need that. Which one felt colder?
I think you're right. Wait, which one do you make ice cream? The hot one. No. Curious. Yeah, the hot one. No. Because it would melt on the cold one. But yeah, because it has to be hotter than ice cream, but like not.
Tell your neighbor why you're seeing what you're seeing.
Because of its thermal stuff. Because it's colder than the.
Oh, poor video kids. Sorry, guys. Totally left you.
You crack me up every day. Like,
No, that was
it's probably the same.
Hello.
This is metal. This is plastic. This felt colder. Crazy.
Oh my gosh, I'm in this video right now. Yes, I was. Yes, I was if I stand up.
All right. So why?
It's colder than the ice.
Which way is heat going?
Out of the thing into the ice cube.
Into the ice. Into the ice. What? No, this is plastic. This is aluminum. Okay. So this is a better conductor. The metal is a better conductor of heat. So heat is leaving the metal faster, going into the ice, causing it to melt faster. Good with that? Okay. All right.
Oh, hello. Not how I expected him to know that.
All right.
Hello?
Have a seat. Hey, here's the question. Does cold transfer? Just heat. Right. Okay. Okay. Next question. Tell your neighbor.
Ask him. Oh, it's cool.
Correct answer is E.
I got the A. I knew I had the
Okay. Now, so like wrap yourself in there. The coat doesn't feel warm because it's warm. It's because you're warm, and it's just slowing down the rate of heat transfer away from you. Air is such a good insulator. Why is that in our houses? Great question. Okay, so E. So, if something's a bad conductor, it's a good insulator. Okay, so when we talk about like insulation in our homes, those are bad conductors of heat, but good insulators. Okay, um, so I'm gonna hit that before I hit your question. Is there such thing as a perfect thermal conductor? No, there is not. Heat will always go from hot to cold. There's nothing that will prevent it from doing that completely. We can slow the rate down. Okay. Um, so when we talk about insulating your homes, the materials that we use trap air. So like fiberglass, the pink cotton candy stuff that you do not want to eat. Okay. Traps air. Foam, like styrofoam, that's a very like not dense material. It traps a lot of air. Good with that.
So like whatever they stuff up goes with was just like the insulator in your house, just not
Back in the day, this is hilarious. Some kids, have you ever down stuffing, down coats, down pillows, down sleeping bags, just like feathers from geese. They're going more synthetic now, but it's just the poofiness just means it can trap a lot of air. Like it's a structure that doesn't get squished. It just springs back so air can stay in it. Get that? We're not going to worry about that. All right. Second way is by convection. Heat is transferred by convection. So um, this is when fluids have different temperatures, causing molecules move faster, and hotter fluids is less dense than colder fluid and floats up, floats on top of colder fluids. So in science, when we say fluid, or specifically in physics, when we say fluid, that could be a liquid, which we're okay with, but it also could be a gas. Anything where the molecules are free to roam around and move is considered a fluid. So, have you heard the expression heat rises? This is that statement is 100% convection. Okay, hot air, um, the molecules are moving more, collide into each other, and so it becomes less dense, and therefore floats on more dense, colder air and rises up. And that's how hot air balloons work. Okay, if you probably haven't had a whole lot of exposure to that, but boiling water, if you ever looked, not like in a microwave, but on a stove top, if there's been any impurities in your water, you could see them, like when they get hot, rise up and then come back down. These are convection currents. Okay, as it rises, it cools down, it sinks back down and heats back up. Okay, convection oven. There's a fan in there that prevents hot air from just settling up there, and the cooler air from on the bottom, it mixes that up, so it's like more, the temperature's more constant, more even throughout the oven box. Here's that. Okay. Everybody good? See? Okay, the reality is this. There are vents in your house. Some are near the floor and some are near the ceiling. One of those is your intake. The other one is the venting out into the room. The other one sucks air back in. Okay. So depending on how your house is built, if your vents on the floor, it does better for heating. But then in the summertime, it uses those same vents to blow out cold air. And so it won't be so good. But if your vents are pushing out air near your ceiling, works well for the summertime, but not so much for the winter. Good with that. You can tell which one's your intake vent, the one that's going to suck the air back to the furnace. It's like a circulatory system. Um, that's the one that has like lint or fuzz on it. That's the one that gets dirty. That's the intake. You can put your hand over it and feel the air sucking by it. So run some HVAC system. There you go. Okay. This is a cool thing. So next time you're at the beach on a hot sunny day, it could be Lake Michigan, it could be the ocean, doesn't really matter. You're going to feel a breeze coming from the water up to land. The reason why is this. Sand has a really low specific heat capacity, touching on chemistry again. It changes its temperature readily. From a physics vernacular point of view, we could say that sand has a really low thermal inertia. It changes its temperature readily, versus water has a very high specific heat capacity. It has a lot of thermal inertia. It doesn't change its temperature readily. That is why in the Midwest, why weather systems influence our climate in crazy ways. Like today we're at 80 degrees, tomorrow we're at 20 degrees. If we were by a large body of water, our climate wouldn't be so crazy because the thermal inertia of the water would stabilize the crazy weather patterns. That makes sense. Okay. So at the beach, sand gets hot fast, right? Water does not. So the hot air, so the sand heats up the air right above it, and that hot air rises leaving some low pressure back here. And so air from the cooler air from the water comes and replaces that. So during the day, you'll get a consistent sea breeze coming in from the water. But then at night, I don't know if you've ever been walking on the beach at night, like after midnight or so, bare feet, sand feels what? Cold. Because it has a low specific heat capacity. It loses, it gets rid of that heat fast, or sorry, it changes its temperature fast. The water maintains its temperature, so it'll actually reverse. There'll be an outgoing breeze during the nighttime. So check that out next time you're at a beach. Okay, you don't have to explain it to anybody, but just be like personal satisfaction. Like, I know why that happens. Okay. All right. Third way is by radiation, thermal radiation. This is where all objects above absolute zero what objects are above absolute zero? Everything. Emits infrared waves due to vibrations due to the vibrations of molecules. Remember when we were talking about electromagnetic spectrum? One of the categories was infrared. This is associated with, or this is the thermal radiation that we're talking about. So, all objects, molecules are vibrating, emit these infrared rays. Okay, you can make something hot enough that it'll actually also emit visible light. That's where you get like red hot. But everything is emitting infrared rays. Okay, good with that. So this is kind of a T-ball pitch here. Very good with radiation. Okay. So we're going to start with this. What describe an object that's a good absorber of radiant energy? CJ. What? I know why you say that. It is dense. That is a good absorber of most electromagnetic waves, just period. This would be dark colored. So black and dull or flat, like a flat, like not glossy. Okay, that's a good absorber. A poor absorber would be a light color. So white and shiny. Uh, Reflective. Okay. A poor absorber is a good reflector. Okay. The classic example of this would be wearing a dark colored t-shirt versus a light colored t-shirt on a hot sunny day. Black's going to be absorbing more. The white is going to be reflecting more. It's a poor absorber. Okay. Now, here is here's the crazy fact that most people don't get this. Whatever is a good absorber is also a good emitter. Whatever is a poor absorber is a poor emitter. So here's what you write in your notes. A good absorber is a good emitter. A good absorber is a good emitter. Poor absorber is a poor emitter. The fact is that all objects are absorbing and emitting radiant energy. Okay. Oop, 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 oop. All right. So here, this is thermal imaging camera that is recording the infrared. Notice on a house, where do we see most of the heat leaving? Windows. Windows have poor insulation values. Even though you can spend tens of thousands of dollars on new windows, they still stink in terms of retaining heat. Notice how it looks hotter at the top than it does on the bottom. Why? Heat rises, and that's JP. That's where your thermal or your heat lightning comes from. Is the heat rising cause those convection currents? Okay. I'm just going to tell you this. If you are colder, no, I'll start with this. If you're hotter than your environment, then you are emitting more than you're absorbing. You're doing both. But if you're hotter than your environment, you're emitting more radiant energy than you're absorbing. If you're colder than your environment, then you're absorbing more radiant energy than you're emitting. Okay? Some examples of this would be wrapping aluminum around food, keep the heat in. Great question, because it's a good thermal conductor, and so it's able to dissipate that heat out into the environment. It reflects the radiant energy back into the food, but itself cools off pretty fast. Okay, so if you ever seen space blankets, like the things they wrap marathon runners around, looks like foil, looks like plastic foil. Um, Radiators, things that the grill in front of your car, it's dull and black. Start has to emit a bunch of radiant energy. So here's something crazy. On a hot sunny day, you're walking across the parking lot barefoot. You're gonna stay on the white lines, right? You don't get burnt. At night, let's say you want to keep your feet warm, and this is like after midnight. Actually, the coldest part of the day is right before the sun rises. because the Earth has a chance to emit a whole bunch of stuff that has more time. So the coldest part of the day is right before sunrise. So let's say you're walking across a parking lot and you want to keep your feet warm. Where should you walk? Black top or white? The white, because the white is a poor absorber, but it's also a poor emitter. The black top will cool off faster because it emits this radiant energy at a higher rate than the white reflective stuff. Whew, good with that. There it is.